all the things have to be modeled, otherwise you cannot make the test sets. And here this is for the field, typically what we have modeled here is Unreal Engine, and you see now what we also can test, what is not possible in real systems. For example, if a tractor is moving on a field, you have this typical vibration. And this vibration can influence the measurement, different types of measurement. Also acceleration sensors and all these things inside. If you have a camera, you get a more wide image based on these vibrations. So, and we like to find out if this strongly influences what more or less our classifier or whatever we do with this image is at the end taken out. Rain, for example, you can really go to a level where you said, oh, what is when rain drops down the lens? What is the effect on an image? Because this is later on, and most of you, I think, come from vision, so you need, you know that the nice data which you use to train our deep learning networks or whatever. And if you, at the end, take these data, you are far away from it. This is always what we said to the vision guys, come to us, go to the real machine, and test different situations, and you see, oh, the classifier drops down from 90 or whatever % of precision to maybe 50. And even this is what we sometimes want it. And this comes with all these effects. Brightness is an interesting effect. Fog, see it on the other side. Where more or less the classification result is tremendously different. And we can simulate this now. This is the nice thing. So we can say, oh, look, what happened in the tractor? Oh, it's not moving. When the sun rises in the morning, runs around and goes down again. And you can now simulate it and can find out what is really, at the end, whatever you want to do in the classification process, the result. And we have made a remarkable test with one YOLO version. We have a camera in the best position looking ahead, and we have 4 simulated persons on the field. And we make just this test. Sun goes around. So we simulate 1,000 or even more images. And we take a standard YOLO, which is not so bad, to classify persons. And now we said count the persons in every of these images. What do you think come out? 4 persons were standing there in the best position. Also from some perspective you get better results as from others, so this was all perfect. So 50% of the time only we count 4 people. We count sometimes 5 people, which also was strange. And then 2, 3, whatever. 1 also, and this comes of course based on the shadow effect. You merge this and the classifier cannot deliver what you have to do. So this is what we now can test. It's hard to test on a real system. How long will you go out and check your system? This is impossible. What we also can use with the simulation, we do this also in an intensive way, is where to place the sensor system. This is a very hard task because if you have a static situation, it's simple. You can place it at this angle, the camera should down, the laser scanner should scan this, fine. But what happened if the machine is moving? And if you have a rough terrain, also we have applications where really the machine is doing this here, then you suddenly find out, oh, it looks to the sky and is doing this here, and the result, what we like to have, is not coming. But to predict this is impossible for you. And this is helping if we have it on the simulation, we can go over it and observe what measurement we get now in the simulation. And we can also find out, is there something what is relevant, what we do not see in a specific situation, based on the position of the sensor. This is also what we now can do. Then for building our software, we have more or less this framework for all of our robots. We use it, of course, also for the tractor. We have our own middleware. We use MachVIS in the group. We have developed a Finrock middleware. It's similar to ROS2 for those who know this a little bit, which supports more or less that you see whatever information is going from module to module. You have a lot of interfaces to sensor, you have the drivers and all these things. You have a nice interface where you can show every camera image and whatever. If you like to use it, you have a widget, you open it and you connect it in a graphical way and you see more or less the results for testing. This is perfect. Then for the control software, we have this reaction architecture. And reaction architecture is more or less here described. It has a typical, or inside the typical control structure, what we have nearly on every robot. We have normally three parts. This is one on one side. It's more or less, you can group it together, the information what you get over the sensor system and the knowledge what we put into the system, the knowledge-based system. Then of course you have user interfaces and you have of course the control part, the red part here, which really controls the machine, and the control in mobile robots is normally a three-layered hierarchical control, what we also have implemented here in the system with navigator, pilot, and low-level control loops, what we also have to implement. This is more or less what we do. And of course, which is extremely important, the fail-safe area, and this is not this emergency stop, this is where really things run on our PC. For example, we detect that a person is coming too close to the tractor, and so we will not start the tractor, because maybe foot goes in or whatever could happen. This comes on a higher level. It's not this what I said before, this emergency stop level where we cannot do anything. On a higher level you cannot switch it off. So this is the problem with this emergency. It will stop. Don't worry. For example, in our bus we have a similar system. We once drive along our campus on a typical pathway, and on one position, whoop, the emergency stop always stops. So what is it? There's no one. Everything is free. Then we find out that our laser scanner is very precise. We measure very small insects. They are like spots, small spot, black spots. You really cannot see it. It's hard to see that. And Hamza makes an experiment on a small wire, and we really measure this, and then we at the end find out, it takes us more than 1 month, why we permanently stop, because this stupid laser scanner really detects this very small spot, this fly, and the emergency stop is active. So these are also things, of course, what is bad, but we cannot change it. So this is, of course, the whole concept. On the lowest side, we have now directly an access of the system to the real hardware, the real machine, tractor in our case. Playback means we can also protocol everything in a test, what we measure on the tractor, all sensor system with a timestamp. Plus, we can measure the control, what we do, what we select in this situation as control. And we use it very often as a playback. So we do not play with the real tractor. We take this measurement data and change the algorithm and look what now is coming. This is what we also do and the simulation that I have explained. So, I skipped this maybe a little bit, the reaction part. I'm not totally out of time. This is more or less our concept, how we can describe more or less our control concept, or also the perception concept. We have more or less two main nodes. This is the behavior node, which is used whatever you do as control. For example, you make a simple collision avoidance, you measure in a specific distance, in a specific angle in an object that you like to drive around. So this could be maybe one of such behaviors where you said, if this is more on the right-hand side, we drive a little bit to the left side because we have maybe the angle between the object and the goal where we like to go. This is normally straight ahead. And so we can make very simple behaviors, reactive behaviors, which are active only if it's a critical situation. If the object is 5 meters away, this will not be active. It's only active if it has to say something. So these are the behaviors. They are structured in a hierarchical way, so we can also go to a social level, use also for behavior base control of our humanoids. Perception is the same, it's also behavior node. Here we do a lot of things in the perception of the environment. Perception is only one thing what we add, because start from the sensor system. What is a nice measurement? And it starts from the quality of the basic measurements of the sensor. So you have an unprecision. For example, take a stereo camera system. So we know if we go in a far distance, the precision goes tremendously down. This is more or less the principle. Depends, of course, on the parameters, what you know, how far is more or less the cameras away from each other, the stereo base, the focal length, and so on, what you have in the cameras. But in principle, you have this. This is not the case if you use a laser scanner. Totally different. So, but now the question is, if you now need a distance image, whatever you like to control, how can we trust this data? Now we have a problem. This trustness depends not only on the principal physical skills of a sensor, it depends also on the task. Which means, if I, for example, drive around, say in 20 meters, I should go roughly to another pathway, and I have a lot of space, even if my stereo system is 5 meters imprecise, I have no problem. Because I first of all go roughly in the direction, later on the precision gets better, so we go better and better. At the end we have only a few centimeter precision to more or less the place what we like to reach. So in this case it's not relevant. If it's really relevant, say you have a car, you drive on the highway with 200 kilometers and the truck is here, and you have unprecision of 100 meters of 20 meters, well, you get a big problem. This is not way. So it depends a little bit on the task what you have, how you interpret the confidence of the sensor measure. And this is what we code here also in this perception. And we can calculate a relative error which consider this task dimension, not only that a sensor has a specific unprecision. And then, of course, because we like to have a big network, we have to have fusion nodes. And the fusion nodes, in our case, is average fusion and the maximum fusion. Maximum fusion is with the activity. So the highest activity says in a behavior, I'm responsible now for whatever we like to do. This is shown by the activity. And based on this activity, if I have a winner takes all fusion, a maximum fusion, the highest activity is selected. The task, what is then done by the machine, is done by the highest activity. So we select then a specific behavior. We can also do average fusion, which means, this is nice, for example, if you have the following situation, think about you have a lot of sensors around your vehicle, and now it's extremely hard to say this is a simple sensor, only like an infrared sensor, only one beam goes out, but you have 20 of this around the vehicle. And now you should say, in a complex scenario, what is now your way how to navigate? And this is nearly impossible. Try it, implement this. Then you find out, oh, for this situation it will not work. So you can do it also the other way around, and this is where this average fusion helps tremendously. You can say, oh, I make regions of around the vehicle, and I said, separate from everything you measured in another region. If in this region something is measured in the close range, I have a specific reaction. And I do it with all other regions, and now the average fusion is coming, which means whatever output is coming, for example, for the steering angle of our Ackermann steered vehicle, we fuse this together, and the fusion is at the end the control result. So this is what comes out, and at the end you get such networks. We have systems where we have more than 600 behavior nodes here inside. We have never defined what is in a behavior node. You can copy a full kinematic model, dynamic model inside. You can, if you have a perception node, also copy a full neural network inside. can have very powerful nodes. It's better to have simple nodes. This is from the concept better because you have an implicit redundancy. So, but you see roughly what comes out. I will not go into detail what is described here. From the functionality, if you drive, I select only this. Path planning, path detection is of course extremely relevant. Here we look not only here for the tractor but also for other vehicles in rough terrain to detect a specific pathway, what you see here, based on the landscape, the 3D terrain description, or based on textures. So on camera system trying to make segmentation of the pathway, because we are not only on street here, it's simple, we are also on touch pathways through forest. If you cross from one part of the field to the next one, or you have pathway which is also hard to detect because everything is green. This is also typically what you find here on fields which you also have to somehow detect. So let's come to the end, more or less. You see now the tractor. This is in simulation where we make now the first test. Now we can, for example, in the collision avoidance, we use here a path planning strategy on the simulated Neumühle. These are the really buildings what you see there. This farm is around 50 kilometers from our university away, so it's nice to go there and test it. And now you can observe under specific condition what your collision avoidance controller, path following controller is doing, and if it's okay, if it goes too close to it. These are typical parameters inside. Sometimes your trajectory goes maybe here to the one too close, and then you get problems if, for example, you have a disturbance in the sensor measurement. This could lead again to critical situation. You see here in this situation you have enough space, you don't have to do this. And on the other hand side, these are the typical transport operations from more or less the farm to the field. This is a hilly environment, and you normally have to go here up to the hill, and on the top of the hill you have the fields. That's why also such a behavior is of course extremely relevant. And now see also the real machine. This was behind our lab. So we have a very small window, and now we can test specific things. We drive to specific points here and so on. So here we make tests, and we do a bigger test. Next week we like to go to the Neumühle, one step ahead, where we drive. This is also on our campus from a specific hall to more or less this small window in a mainly autonomous way. So we control per hand over the street, because if something goes wrong, we have a big problem. But on this other pathway, it goes. See this how the tractor now is navigating. This is parking sites around our lab. It crosses. This is the official street. In Germany, not allowed even with a test machine to drive over or on it. This is the principal problem. Of course, we do it, but this is by law also not never. They catch us. This is here the parking area of the university. Here it's not so critical. It's a private area, or half private we call it. If something happens, we get also a problem. But this is normally very safe. This is also robust. If someone jumps ahead, it will directly stop. And so here with also this speed, not too much can really happen. We go now maximum 10 kilometers per hour. In the normal test, this is around 5 kilometers per hour, something like this. And then the brake distance, if an emergency stop is coming, these are some centimeters. This is real, so I would say 40 centimeters, something like this. So direct distance. This is the advantage that we have. Okay, this brings me to the end. These were more or less the result what I introduced. We have to add a lot of things what we have implemented for other machines, and also define a few new things. But we hope that we sure that we can do typical operations on the Neumühle on this farm in an autonomous way. So this is what we think in a short period of time we can show also in fields. So thank you very much for your attention. I hope I was not too long.
So can we have some questions now? Okay. Before anyone asks, I want to know something. What do you think about introducing crowd control or rather crowdsourced data into these simulations? So I see, especially on Steam, people already have farm simulators which are very popular, and there are lots of gamers around the world which play this. Why don't you release the same thing for the general population? Once they play, you get some kind of decision making from them. No. Then you apply some kind of things on it.
No, get it not. We also know this nice farm simulator, and we also check it. What you have to implement, and that's why you have to have an open system, is that you have the possibility to extend your system. For example, with the sensor system. You have no sensor system in these games. And even if they have a standard sensor system, look for Kala. I don't know if this is known. This is for cars. You also use Unreal Engine and add a layer on it, and they have it only for streets and whatever. Even if you look, they have simulated more or less the sensor system in a very bad. We have compared to what we have done, and then you see differences. Because, for example, what is inside this Unreal, only to say not too much technical details. There is a simple set buffer. Set buffer gives you a distance information to the object. But it says nothing if something is in between. Which means you have to have a ray tracing concept if you really like to understand what your sensor is measuring. And then it gets harder. And the nice thing what we have is we can now implement in this engine the physical properties of such a sensor. Of course, it's not one-to-one, this is impossible, but you can go much closer to the real sensor measurement. And this is, of course, in the games not existent, even as I said, in the tools there are a lot of problems with the sensors. And of course, we like to be flexible. This is also, if you have a tool, you are not flexible, you have what you have. But we like really also for application and construction say, oh yeah, this is our place where we like to do something specific. And let's go measure this and bring it to the simulation. And this is the next thing where with standard tools you can do this. You must have the control on all these things, otherwise you will fail. It's too far away from you. Looks good, definitely. We have also checked this. We can also use the bar. It's really good, it's nice. But of course, for example, also shadow effects is not so perfect as here. They calculate much better. Of course, also these games are based on these tools. But it's clear how should you do it.
I was just curious to know that these simulation software that your group is using, these obviously have matured over the years. So how are the development steps like 15 years ago when these simulation softwares were not so realistic?
Yeah, so we started when I was in Karlsruhe, we built the first simple simulator. I remember it in the 90s. And this was only lines and such things. This was maximum what is possible. And what you see really in this tool you can as a video. And of course, to make this is not only from the conceptual point of view, a lot of things which were now getting better and better. It's the computing power, what we never had in the past. So, and now we have enough computing power to, we have never enough computing power, but to make this very nice simulations. There are also defined as about Unreal videos in the internet where you really compare. I have done it with students. I show an Unreal video and a real video. There's a nice one from a forest. And I said, is this a real video? Is this a simulated one? And they do not know. This is directly coming out. If I said some is simulated, then they guess. But you really do not see it anymore. But you must be careful. This is not what we need. Not only the appearance is interesting, we have also other sensors. We have to simulate the physics of the system. And of course, this is much harder to do. But also here, a lot of things go to make this also more realistic. For example, how is the tractor behaving? What they do in these games is, it looks nice. That's all what you need to play by yourself. But looks nice is not the physical behavior of a real machine. And we have also to come closer to it. Now, so we have also now started with these more physical tools where they calculate roughly the dynamics. So for example, that you have mass distribution. And if, for example, you have a car and the motor is in front, the mass distribution is more in the front. And if you jump, it falls in this way down. And if it's in the back side, it falls in this way down. And this is of course important later on if you like to use it as a testing one. And of course here they have to add more and more and more. And now again we have computing problems. Now we are on the limit. Batteries are such things. Even if it would be nice, there are tools, but they calculate hours to give a result. That you said, okay, what is more or less the behavior of the axis? What forces now can be measured in the simulated axis? But then we are far away from what we are doing because for simple movement it takes hours to calculate this. And we like to go, of course, closer to this movement. But it's a long way, but we have now reached a situation, what I have never seen in my life, that we get so realistic this machine simulated. It was never before.
First of all, thank you, Professor, for your insights. And I want to have some look on smart farming 4.0. Is that related to industry 4.0 and 5.0? And second question would be related to your product, because I am a son of farmer and I have an experience of using tractor. I see your product is more on checks and brakes, which is more sensitive. It would rather, limit its performance in terms of flowing and field work, which would be, if it would be to the industry level or factory level, then how would you incorporate that performance limitation in your product?
The idea is that we get rid of the persons. You must be careful. If you have an assistance system, you have it in the cars, this is well known. And you implement a assistance system where you have in mind, there's a farmer driving, and only in a specific situation the system is doing a little bit. You will never get an autonomous system, I'm quite sure. So we always think there's no guide. And the system is making the decision. So we like to take it out for our research. You are right, this is what John Deere is doing. You can buy a lot of big tractors. You have, for example, follow pathway with GPS, very, very precise. They have a precision of 1 to 2 centimeter if you have enough satellites, what you see. Otherwise, it's a lie. But they can do a lot of the standard operation on the farm, but they have to guarantee there's a person sitting there. If you like to get rid of the person, you have to implement in a totally different way. And we are not interested for assistance systems. We directly jump on autonomous systems. So we have not the problem that someone is doing something. If you have it, you have to look strongly for the interfaces. How does this look? It's also not a simple task, because you need a little bit time to take over the control again. So normally you calculate up to 20 seconds in cars, they measure it, to analyze the scenario around the car. Think about, you read the newspaper and now the red button is coming, you should take over the control. Then they measure about 20 seconds, which is a long time to calculate how long you can drive in this period. Of course, you can make a reaction where you see a next object directly next to you faster, but to analyze the scenario to make a nice decision takes longer. And this is also a hard problem, but we are not interested.
And about my first question, smart farming for have your examples?
Yeah, all these things goes more or less into this smart farming. What happened at the moment, because we are strongly together with John Deere, so we know a little bit what they are doing and try to implement for the next years. What the idea of all these companies is, they like to give you services. So there are ways that they sell a tractor. This is what you can forget in the future. They sell services. And the services is maybe related with a tractor, with an implement on the tractor, with a specific task, with a specific environment. And now the cloud things come. They have all cloud services. And of course you should also pay for it. You download the services to a platform which knows what to do with the services. And then you get this task, of course, at the moment, as I said, you as a farmer, you have to drive with this vehicle and make swaps or whatever. This is not what they like to automate now. This is by law a big problem. But they really like to sell services. And it's also not only the tractor, also these digital systems around, these databases, these knowledge bases, all is what they like to combine to each other, so that you, at the end, as a farmer, this is also only for big farms, not for small ones, forget it. All these tools you can forget, you cannot use for small farms. So, but for big farms, maybe you can reduce the man effort tremendously with such tools.
What is the basic goal in this? We see the navigation and so on. Is there any digging bucket or a blower should be attached with this, and then
we have at the moment no implement. We order a cheap one, which is not so expensive, we have to pay it. On front, this is a mowing unit.
mowing? Yeah.
But as I said, we have infinite implements which you can buy. And of course, you have to do, we have another idea, but
Because just
it's too long.
if the application is, for example, for mowing, then the navigation should be a bit different than
Has to be
compared
adapted.
Yeah, it
You're
should be
right.
adapted. That's what I.
Yeah, and then also the mowing unit has to be adapted.
Exactly.
And how do they do it today? They have a nice bus system, standard, where also the guys who build the implements, these are not normally the tractor companies, and the tractor companies can communicate with each other with interbuses. This needs that you have a big effort, because the tractor have to know if I'm over here the plant that you should have maybe 3 meters the mowing unit ahead, so you have somehow to calculate what must be my behavior so that I will not also mow the nice flowers or whatever.
Yeah.
So and this is not simple.
Yes.
So what we try also in internal other project for PhD is we like to separate. So you said you have an intelligent implement and intelligent tractor or whatever machine, and there's nearly no communication between each other. They both know the task. That's all. This is the same if you think about people. Say you have one person sitting on the tractor and another person, whatever you can control, will control this mowing unit. And it works. Quite sure it works. And they don't have to have communication between each other, because maybe the mowing unit says, oh, now the tractor or my unit goes over the flowers, so I lift this mowing unit. So I don't know what the tractor is doing, I cannot influence, but I can lift and then we have no damage. And a similar thing is what the tractor driver can do. And we also like to test this, that we have really a distributed system.